So the third example of utility functions is going to be, a shape we haven't seen before. These are going to be quasi-linear preferences. So as the name suggests, so this is a shape we haven't seen before. And as the name suggests, it's like partly linear. So for example, it's linear in, let's say good 2, but let's say possibly nonlinear in good 1. So let's maybe write it mathematically down here and kind of talk about the shape and make sure we understand kind of why this is the function for this kind of shape. So let's say that u of x1, x2 equals v of x1 plus x2. So v is some like function, some possibly nonlinear function where the utility is linear in good 2 here. So if we want to draw difference curves, that would mean v1 plus x2 equals some constant, right? And then we're going to draw the different combinations of x1 and x2 that are, where these two things add up to this constant. So if we rearrange this, we want x2 as a function of x1. So we're going to move that to the other side. It's going to look like this, right? So this is essentially kind of like what we're drawing out for our difference curves. So if x equals 0, x2 equals k. And then there's some, as we add more x1, that's going to change the shape a bit. Hopefully that makes somewhat sense what I'm trying to get across here. So here's x2 and x1. And so let's say if x1 equals 0, and who knows what k we're on some k here. Whatever this number is. And then it kind of like looks like this. Right, and then we have another k, let's say this is 1 and this is 2, where, they're like kind of vertical, you're kind of shifting up the same vertical thing, same indifference curve, kind of like vertically, right? It's vertically shifted, I think that's what the textbook says, so let's write that out. Vertically shifted. Versions of an indifference curve. Hopefully you can kind of go from here to here, right? It's linear in x2, but non-linear in x1. It probably shouldn't like loop up like that. It should be like continuing down in this direction. But so that's the idea of these quasi-linear. And so I mean this v function could be any kind of non-linear. It could be like the square root of x1, or it could be the ln of x1, or whatever. Like it could be any nonlinear version, like any nonlinear function. We're not going to see this a ton in terms of these nonlinearities, but these kind of preferences could come up as we kind of move our way through the course. So the final example of a difference curve, so I think this is number 4, are going to be Cobb-Douglas, and we're going to see a lot of these this semester. Just has some nice properties that we might want. And so for Cobb-Douglas, the form of these Cobb-Douglas, so x1, x2, so here's the utility function, is going to be x1 to the power of c and x2 to the power of d, where c and d are positive numbers. So we're going to use this frequently, and they kind of have these like really nice shapes to them. These like really nice, like well-behaved, monotonic convex shapes, these indifference curves. So they look like nice, well-behaved. Remember we talked about well-behaved preferences last chapter, or indifference curves last chapter. So they look like well-behaved indifference curves. So they're like monotonic and convex. And so if we want to, to draw a couple examples or use different numbers for C and D, they're going to look like kind of these the classic indifference curves that we might have drawn in first year or kind of when we drew these well-behaved ones. So let's say if they each equal 1/2, they kind of have this like nice little bow shaped to them, something like that. Whereas if C equals 1/5 and D equals 4/5, and we'll talk about you might see a pattern in terms of what these exponents add up to, and we're going to come back to that for a second. We might have slightly different preferences. They're just like flatter in this one because there's kind of like the exponent for good 2 is a little bit higher, so it just kind of changes the shape a little bit. But again, they're nice and convex. It's not like you have to be able to like, I'm not going to give you some exponents and ask you to draw them or something like that, right? I'm just giving you an idea of what a utility function like this looks like in terms of indifference curves. So here's our Cobb-Douglas again. I just kind of erased down here so we still have this up here. So again, any monotonic transformation of this utility function kind of maintains those preferences. Can be used. And so let's look at a couple different examples. And the second example is something we're going to see over and over again, and maybe why we had them add up to 1. These exponents add up to 1 before. So let's think of 1, which is, again, let's just use B as this monotonic transformation, and what we could do is just take the log of x1c and x2d. So that's the monotonic transformation that we're assigning. This is the monotonic function, is like the log of this old utility function. And we just use our log rules, and we have this d times ln, natural log, right? And so that represents the same preferences as this original one. We're just like relabeling these indifference curves. So the second kind of example is that basically we can always do a monotonic transformation to make these exponents add to 1. And that's going to end up being useful later because it's going to have certain properties we might like. So if we want to like, let's say raise to the power 1 over c plus d. That's what we're going to do to this original utility function. That's the transformation we're going to make. We're going to raise it to the power of 1 over c plus d. Well then, our new utility function, whatever we want to call it, we can call it b again if we want, is going to be x1 to the c plus d, x2 over d over c plus d. And then we can just kind of redefine what these exponents are. So this is just equal to x to the power of a, so x1, sorry, to the power of a, and x2 to the power of 1 minus a, where a equals c over c plus d. And so notice this is kind of like the form we had with the 1/2, right? If a was 1/2 in that original drawing that I did over here of the indifference curves, and so the power, d was 1/2, so it was 1 minus 1/2, which is 1/2. So it's kind of like we noticed that they were adding up to 1 before. We can always make this true, I should say. So it can always make exponents add to 1, and this is going to be useful. Might not be clear now, but we're going to talk about this in a bit. All right, so that's the Cobb-Douglas. We're going to be using them a lot. So we should kind of understand what they're doing, kind of realize that we can always make the exponents add up to 1 with a monotonic transformation, which maintains the preferences from this original utility function.